Geologic time is a topic that I really dig because it has to do with the rock record. You have to dig to see the rocks. Anyway, I hope you enjoyed this chapter 29 material. Pay particular attention to the first paragraph there on page 690 where they describe the length of Earth history, essentially 4.5 billion years in the making. And what if we could put it out on one calendar year? So that means the formation of the Earth 4.5 billion years ago, January 1st. And that would mean that Homo sapiens, the emergence of Homo sapiens, which was about 100,000, maybe 250,000 years ago, would be the last 10 minutes of that calendar year, December 31st at 11:50 p.m. And the time period of modern humans and recorded history, last couple thousand years, that would be the last minute of that entire year. That's pretty fascinating. And another analogy is on page figure 2911 in the textbook, page 701, where they put, instead of on a calendar year, they put it on a clock. And that's actually one of the skills tests you're going to wind up doing is the geologic clock and trying to assign the different periods of development of life to that geologic clock. Anyway, I hope you find it all very interesting. So as was just mentioned, you can lay the entire history of the Earth onto a calendar, and here's some of the, sort of the important dates. Of course, the Earth forming then 4.5 billion years ago, but also in this case it would be January 1st. But check out how long there was really not a whole lot happening. And when we think about the dinosaurs, we think about the dinosaurs living so long ago. But in this depiction of Earth history, they were a relatively recent life form and relatively short-lived life form. And of course, as was mentioned already, human history is really just a minute on this overall time scale. Now, how do we get ages of things from the rock record? As you're going to discover, there's two different ways of dating rocks. Relative dating, which essentially is you're able to tell which rock layer is older than another, but you can't come up with an absolute date. You can just kind of relative to each other. This one's younger, this one's older, this one's older still, but you don't have actual numbers, how long ago those rocks were formed. Radiometric dating is a way of using a scientific measurement to determine the exact age of rocks. So you're actually coming up with numbers as opposed to just relative age. Now, there's a couple of principles of relative dating that are mentioned in the first section of this chapter. So this is chapter 29.1. And they involve horizontality, superposition, and cross-cutting. So you want to make sure you understand those as you're going through the material, and that's going to help you in doing the first skills test. Actually, one of the lab activity actually of the module. A couple of other things: inclusion. Inclusion is anytime you have a different type of rock moving into a rock layer. Lateral continuity, as well as faunal succession. Lateral continuity means that even if you have separate rock outcrops, if you have similar layer structure, even if a river came through and cut a big channel, such as like in the Grand Canyon, you have continuity. The layers on one side are essentially the same order as the layers on another. So they were all one layer at one time, and then the Colorado River cut the big channel in the middle. Same thing with faunal succession, is you can have similar layers of fossils, perhaps even in separate continents. And that just means that the continents had drifted apart. So that you can see lateral continuity when it comes to forms of life as well. Now, before you get the impression that relative dating is really easy, that it's just like a birthday cake where the layer on the bottom is the oldest, and then the icing in the middle, and then building the birthday cake, you put the bottom layer down first, and so forth and so on. Life's not that easy. A lot of things can happen in life, right? And that's what happens with the rock record, is that it's not just a bunch of horizontal layers where the deepest one is the oldest and the one at the top is the most recent. There's all kinds of things that can happen, whether it's folding of layers, due to mountain building. You can have magma intrusions. You can have earthquakes and breaks in the layers. You know, sedimentation that occurs. So all these things show up as unconformities, which make reading the rock record a little more complex, but not impossible. And you're going to use your knowledge of the principles of relative dating, as well as your knowledge of some of these unconformities, to tackle the lab activity. It's called reading the rock record, and you're going to be challenged to put, you'll be given some diagrams of rock layers, and you'll be challenged to determine which is the youngest, which is the oldest, what happened in between. The topic of radiometric dating is not a new one. We actually covered this back in Module 2 when we talked about radioactive half-life. And essentially that's what's going on. In order to determine the actual age of stuff, rather than just the relative age, you can use some of the radioactive materials in rock. And by judging how much of the daughter isotopes there are and how much of the parent isotopes there are, you can determine the roughly exact age of rock. Okay, so this is the big chart that shows kind of lays out geologic time. One thing I really want to point out to you is this right-hand column here, that MA. What does that stand for? That stands for mega annum, or millions of years. So therefore, if we really look back, you know, the eons can be divided into just two. There's the Phanerozoic and there's Precambrian. And notice where the dividing line is. About 543 million years ago, which is nothing. That's a half a billion years. So the Earth's history, which is 4.5 billion years in the making, you know, what we really have a lot of information about is only stuff that happened in the last 0.5 billion years, half a billion years. The other 4 million there's not a whole lot of information. And it's kind of compressed here in this scale, or in this diagram. You can see that most of the attention is given to the last half billion years, which makes sense because that's when the real macroscopic life sort of started to come to the fore. So the Precambrian, which took up a huge portion of the overall history of the Earth, remember, essentially was 4.5 billion years ago to about a half a billion years ago. So that's about 4 billion years. A lot of the Earth's history is wrapped up in the Precambrian. As far as the history of life, well, not that much. A lot of simple organisms were around at that time, but they were all mostly soft-bodied, so not a whole lot in the way of the fossil record of these organisms, but they were essential to the later development of more complex life here on Earth. As was mentioned in the Precambrian, because of the soft-bodied nature of most of the organisms, there wasn't a whole lot of fossils, but the fossil records that do exist indicate that there were these very important organisms called stromatolites, and they were pretty simple organisms, but they would build these massive colonies, which have been fossilized. And then, as the Precambrian continued, more multi-celled organisms and a larger variety of organisms came into being. Okay, as the Earth cooled and as these early forms of life evolved primitive forms of photosynthesis, oxygen became a bigger deal, which was great. Well, it transformed the Earth's atmosphere and did set the stage for more complex life to evolve after the Precambrian, as we went into the Phanerozoic. The history of life on Earth becomes much more interesting as we move into the Paleozoic Era. As you notice, there are 6 periods, and that means there was 6 periods of major changes in life. There was first continents started to be formed. There was several climatic changes and rises and fall of sea level, and this all helped to increase the amount of diversity of life on Earth. Okay, so if you remember, the Paleozoic Era essentially consisted of 6 time periods, and I really can't do any better than the book does as far as detailing these different periods. So I encourage you to just kind of read this whole section. and really pay attention to what makes one period different than the other. And not only the type of life that emerged and evolved during these different periods, but the root causes. Why did life evolve during a particular period? And largely, quite often, it had to do with the distribution of land on the Earth. And so notice in this image we see Gondwana land near the pole, and then we see some of the continents, North America, parts of Asia, being close to the equator. And so the distribution of land mass on the Earth's face had a big impact on the climate. And the climate, whether it's an ice age or whether it's a warm period, would affect the type of animal life and plant life that evolved and emerged during those periods. So you really just kind of read through this section, keeping that in mind. I will mention here the Carboniferous period that there's mention about the fact that this was when fossil fuels really came to the fore. There was a lot of plant life, especially across North America, Africa, parts of Asia. And they even mentioned the Mississippian period and the Pennsylvanian period, which I think is very interesting because I'm a Pennsylvanian who lives in Mississippi. But anyway, keep that in mind. And of course, then the Permian period was sort of the end of this Paleozoic era. And essentially, a lot of the species became extinct. The great Permian extinction occurred. And keep in mind, what are the possible causes, what are the root causes for that mass extinction? Okay, so now we get into the Mesozoic Era, the age of reptiles, divided into the Triassic, the Jurassic, and the Cretaceous. So obviously, when you hear the term Jurassic, you're thinking dinosaurs. So we had an emergence of land species, particularly land reptiles. And again, the book is going to be your main source as far as the details. Now, one thing I will mention is that the fossil record is so much more rich during this time period, so this is why we have a lot more detail about the evolution of species during the Mesozoic era. And of course, this continued on until about 65 million years ago, when essentially the dinosaurs dropped off from the fossil record for the most part, with the exception, of course, of birds, which are indeed just feathered dinosaurs. Now, the Cretaceous extinction then paved the way for the Cenozoic era. So what was the age of reptiles then paved the way for the age of mammals. And again, your book does a good job detailing some of the major developments during this more recent time period. And certainly the ongoing changes in climate have really been the drivers behind a lot of the evolution of the species during the Cenozoic era. Okay, so now that you've learned a lot about geologic time, you can kind of put it all in perspective, do the deep time skills test. Again, it's a little simulation that has the evolution of life here on Earth, part of a clock, a 12-hour clock. And again, there's a little video tutorial which will help you in navigating your way through the skills test. And finally, the readiness assurance test answers for Chapter 29.